Okay, as we discussed in class, we have two theorems that kind of work hand in hand, mean value theorem and Rolle's theorem. And these first two examples I'm going to work through, mean value theorem, and then Rolle's theorem we'll do with 3, 4, and 5. So problem number 1, let's just get a quick little sketch of this. So we know we have a y-intercept at -2. We have a downward parabola. We're looking at the point 2. So if I stick in 2, I get a -4, +4, -2. So I have a -2 here. So my parabola must look like something like that. So basically, the mean value theorem says if I have the derivative of c, that's going to equal the slope between these 2 points. Okay, so let's draw the slope between point A and point B. So in this case, it's kind of unique. It's a straight line, which means that the slope will be equal to 0. So what we're going to do is somewhere along in this point A and B, there's a point C such that we'll have the same exact slope. So the process that you want to do is take the first derivative. So we take the first derivative, and the first derivative is -2x plus 2. And then the second step is you want to set it equal to this slope. So since we found that that was equal to 0, then we'll find the x where that equals the case. So when x equals 1, the slope will be exactly what the slope of the secant was between those 2 points. So when we find the values of c that satisfy the mean value theorem, in this case, c would equal a +1. And we can kind of see that. So the second example is a little bit tougher. So again, let's find, we want to find f of b minus f of a all over b minus a, where this is our b and this is our a. So the first thing that we have to do is let's plug in what 3 is. So f of 3 will equal 9 minus 4 all over 6, or 5, 6. F of 1 will equal 1 minus 4 all over 2, which will equal a -3/2. So we first have to find the slope of the secant between these 2 points. So 5, 6 minus a -3/2 all over 3 minus 1. So let's get a common denominator. Common denominator would be 6. So we have 14, 12, or 14, let's see, 9, 14, 6. We divide that by 2, which is multiplying by 1/2. So we get 14 twelfths. Let's reduce that as 7 6. So now our step is to set the derivative and find out where the derivative or the slope of the tangent equals exactly 7 6. So if we look back at this equation, x squared minus 4 all over 2x, we could do p over q, but let's, since we can separate, let's rewrite this as x squared over 2x minus 4 over 2x. So again, that looks like what? X squared over 2x would be 1/2 x. This simplified will be -2, and then x to the -1. So we're charged with finding the first derivative. So the first derivative, 1/2 x, would be just 1/2. Taking the derivative of 2x to the -1, bring down the power, take it to the 1 less power. And then, once we do that, we must set this equal to 7 6. So to set a fraction equal to a fraction, it might make sense to get a common denominator here. which let's make our common denominator 2x squared. So we have a x squared here. This needs a 2, so we'll have a 4. Setting this equal to 7/6, a fraction equal to a fraction, we'll cross multiply. So we'll get a 6x squared plus 24 equals 14x squared. Remember, we're finding x squared. So we get 24 equals 8x squared, or x squared will equal 3. So where is it that the derivative will equal 7/6 when x equals a positive or a minus the square root of 3? So let's look at, in this region, our two possible values are the square root of 3 and a minus square root of 3, but positive square root of 3 is the only one that's in this interval. So final answer will be the square root of 3. And then when we get into class, I'll show you what this looks like fractionally. When we graph it, I'll show you how we can verify this. Rolle's theorem is an extension of the mean value theorem. And basically, what you want to do in order for Rolle's theorem to hold out, you want to check that f of a equals f of b. And if those equal each other, then what Rolle's theorem says is there's some number in between b and a, we'll call that c, where the derivative equals 0. Okay. So again, looking at this, we might graph this real quickly. If I put in a 0, I get a 1. If I put in a -1, I think I get a 3. If I put in a 2, I get a 3 as well. And our graph kind of looks like this. And so if we see that these function values are the same, then there's somewhere where the derivative will equal 0. Okay, so let's go find that. So first of all, let's take the first derivative. So the first derivative is equal to minus 3x squared plus 4x plus 1. And then since this is a quadratic, we've got to set this equal to 0. So remembering quadratic formula, let's plug in what we know. So the opposite of positive 4 is a minus 4, plus or minus the square root of 4 squared minus 4ac all over 2a. I'm going to try to simplify this. So we get a minus 4 plus or minus 16 minus a minus 12 is a 28 all over -6. And then let's rewrite this as minus 4, 6 plus or minus. You should recognize that 28 has a perfect square root of 4. How do we simplify this? -4 over -6 is 2/3 plus or minus. This becomes 2 square roots of 7 all over -6. So this would be plus or minus 2/6 reduces to 1/3. So where is it that the derivative will equal 0? At 2 plus or minus square root of 7 all over 3. Okay. And again, we'll take a look at that when we're looking at our graphing calculator. But if we don't have a graphing calculator, let's look at the region. The region in between -1 and -2, or +2, we only have to look at the two values.